In August 2025, during the SEG AEPG image meeting in Houston, Mr. Johnson with Magnet Geological joined a Geoscientists Without Borders field trip to Matagorda Beach on the central Texas coast. The project is called Building Resilient Coastal Communities at Matagorda Bay. It brings together university researchers, students, and volunteers to understand how this barrier island system is changing and how that change affects nearby communities, habitats, and infrastructure. At Magnet Geological, we provide geological assistance to a global community. Our primary audience is investors and lenders, but we also work with engineers, floodplain managers, environmental firms, and anyone else who has a stake in the land. During this field trip, Mr. Johnson offered to provide a mineralogical and geochemical evaluation for Mr. Collier, who is working on his graduate degree from the University of Houston with a project at this location. In this video, we will walk through one detailed example from the Texas Gulf Coast, using two sand samples from Matagorda. One sample comes from the active surf zone, and the other comes from the back beach dunes. To understand the setting, we need to review the currents and sedimentation. Along the Gulf Coast, a network of rivers and streams sheds sediment off the continent and out across the coastal plain. These rivers deliver sand, silt, and clay to the shoreline and into the shallow Gulf. Once those grains reach the coast, they do not stay put. Waves and nearshore currents pick them up, move them along the beach, and carry them offshore. In plan view, you can imagine pulses of sediment leaving each river mouth, then being swept along the shore by longshore currents, or carried outward into deeper water by storms and circulation patterns. Some of that material is effectively lost to the deep Gulf and does not return on human timescales. Some of it, however, is reworked along the coast, building and modifying barrier islands, spits, and tidal inlets. That constant tug of war between supply and removal is the backdrop for our field area. Now we zoom into Matagorda Beach itself, located on a barrier island just up current of the modern mouth of the Colorado River. From this scale, you can see how the barrier island, the tidal inlets, and the river mouth line up relative to the open Gulf and the bay behind the island. Our field site sits right where longshore transport, river discharge, and engineered structures all intersect. Zooming in again, the modern mouth of the Colorado River comes into focus. This is not a purely natural inlet. It is a manufactured and repeatedly re-engineered mouth, bounded by jetties and river walls designed to hold the channel in place and keep it from migrating down drift along the barrier island. The circle marks the area where we collected our samples and where the geophysical crews worked during the field trip. Right on the open ocean side of the inlet, within the active swash zone and adjacent dunes. This photo shows the field area on the day of the trip. You can see the pier, the active beach, and low four dunes in the foreground, with the near-surface geophysics team and a drone capturing imagery and elevation data over the site. Next, we are going to follow the recent geologic history of the sample locations, but to refresh your memory on sample locations. Marine sample, taken within the tidal and wave-dominated swash zone on the open beach, where waves constantly stir and sort the sand. Dune sample, taken on the leeward side of an aeolian dune, where wind, rather than waves, has concentrated and reworked the sediment. These two samples sit only a short distance apart in space, but they occupy very different positions in the coastal transport system, one in the energetic marine environment, and one in a more sheltered, wind-dominated setting. That contrast will be important when we look at the mineralogy and geochemistry later. Note how the sample environment changes through time in the following sequence. Historical evolution of the inlet. To put our one-day snapshot into context, we can step back through time using historical imagery. The first image, from 1943, shows the Matagorda barrier island and the mouth of the Colorado River before major geotechnical modifications. The inlet and shoreline are relatively free to migrate, adjusting to storms, river floods, and longshore currents. By 1995, a jetty has been constructed up current of the river mouth. The likely goal was to stabilize the inlet, protecting navigation and reducing the tendency for the channel to drift along the beach. By 2008, we can see that the single jetty solution had problems. The downcurrent side of the structure shows pronounced deposition, evidence that wave energy and currents have been altered in a way that promotes sediment accumulation and local shoaling. In trying to fix one part of the system, we change the sediment pathways elsewhere. In the 2018 imagery, a new configuration appears. Parallel seawalls or river walls now confine the mouth of the Colorado. These twin structures further discipline the river, focusing flow and trying to keep the entrance open while managing adjacent erosion and deposition. As mentioned before, our sampling strategy in plan view was simple: one sample from the marine swash environment and one from the dune environment. In the stratigraphic sense, we chose surface sediments because they represent the present day. Based on the Google Earth imagery, that surface expression has been stable from at least 2018 up to the time the samples were collected in 2025, so these deposits are modern, time-equivalent slices of the same coastal system. In other words, they are chronostratigraphic equivalents, different environments formed over the same interval of time. In principle, we could also dig deeper to find another chronostratigraphic marker, such as a hurricane washover layer or other event horizon, and compare that deeper storm surface to today's active beach and dune. But for now we will just look at the current geology, mineralogy, and geochemistry. Note that through this video we often use these results as an example. We don't intend or suggest the use of the Matagorda area for development or agriculture purposes. In evaluating the two samples, first we will begin with texture and grain size distribution. The simplest question to ask first is, what is the texture? In both samples, the answer is almost pure sand. The marine sample is about 95% sand and about 5% clay, with no gravel and no silt. The dune sample is very similar, about 96% sand and about 4% clay, again with no gravel and no silt. So the beach and the dune are clearly part of the same sandy conveyor belt. This is not a story of sand in one place and mud in another. The differences we are about to see are about how that sand is sorted, how it is packed, and what minerals it carries. When we break the sand down by grain size, the two stories start to separate. In the marine sample, most of the grains fall into two size classes. About 3/4 of the sand is fine, around 0.25 millimeters. Almost 1/4 is medium sand, around 0.5 millimeters. A tiny remainder is slightly coarser or finer, but only in trace amounts. If you plot that distribution, it has a bimodal character, two favored grain sizes. That makes sense in the swash zone. Every wave that runs up the beach and flows back down is a small sorting experiment. Lighter grains move differently than heavier grains. Fine sand and medium sand respond differently to the same wave. Over thousands of waves, that constant reworking leaves a mixed but patterned sand body. Fine and medium sand together, always in motion. This plot compares the marine swash zone sample with an ideal well-graded sand. The gray line shows the textbook well-graded curve. The blue line shows the actual beach sand. In a well-graded material, the curve rises smoothly, indicating that many different grain sizes are present. In the marine sand, the blue curve remains flat through the finer sizes and then climbs steeply over a relatively narrow band of sand. The D10, D30, and D60 points, the grain sizes at 10, 30, and 60% passing, are closely stacked together. This tells us that there are no silts and no gravels, and only a trace of very fine material. Almost all of the grains fall into a fairly narrow sand window, with only a modest tail toward coarser sizes. In engineering terms, this is an SP sand, a poorly graded sand that is easy to compact but does not interlock the way a well-graded sand would. Investors and lenders should hear that as follows. This material will compact, but under stress it will behave more like a glass bead pack than like a mixed soil. Under flood loading or traffic loading, it can rearrange and lose strength if it is not treated correctly. From a functional standpoint, this is a two-size sand. It drains rapidly, it offers little cohesion, and it does not naturally trap fines or organic matter. A developer might see this as easy working material for grading and shaping, but the same data warn a lender or an insurer that, under high water, this is a loose, non-cohesive medium that can scour and lose bearing capacity. The dune sample tells a much sharper tale. Here, nearly all of the sand, about 97%, is concentrated in a single size class at 0.25 millimeters. Only about 1% of the grains are at 0.5 millimeters, and the very fine tail below about 1/10 of a millimeter is barely present. When you compare the dune curve to what engineers call a well-graded material, where you hope for a nice, even spread of sizes, this dune is the opposite. It is narrowly sorted. The grains are almost all the same size. That is exactly what we expect from wind-worked sand. Aeolian dunes are efficient natural sieves. Wind has a preferred grain size that it can pick up, carry, and drop most easily. Over time, the wind strips out the extremes and piles up one favored size. At Matagorda, the dune is taking the mixed beach sand coming off the marine conveyor belt and turning it into a single-size, wind-refined product. The dune sand starts from the same source but has been resorted by wind. The dune curve rises even more steeply than the marine curve. The D10, D30, and D60 points almost coincide. This is what a highly uniform sand looks like. The dune pie chart shows that about 97% of the sample is quarter-millimeter sand, with only a very thin tail towards slightly coarser and slightly finer sizes. As with the marine sand, there is no gravel, no silt, and only about 4% clay in the full texture. Grain size and sorting are not just academic details. They control how much empty space exists between grains and how easily fluids move through that framework. That is porosity and permeability. For the marine sample, the estimated porosity is about 38 to 42%. Close to 2/5 of the volume is pore space. The estimated permeability is on the order of 800 millidarcies. For coastal hydrogeology, that is a very conductive sand. Water poured onto this material at the surface will not linger. It can move quickly downward and sideways. For the dune sand, porosity steps into the mid-0.4 range, and permeability climbs into and above 1 darcy. The dune sample porosity falls in the 44 to 48% range. For unconsolidated sands, around 45% porosity is often treated as the practical upper limit for random grain packings. This dune sits right at that high-end zone. Its estimated permeability is roughly 1.7 darcies, about twice that of the marine sand. When grains are all about the same size and there are very few fines, pore spaces line up and connect more easily. The dune becomes a high-capacity, high-throughput reservoir. As we move into the mineralogy, again remember the marine sample is within the wave and tidal zone and that affects the mineralogy. The marine sand is approximately 91% quartz. It contains about 2.5% plagioclase, about 2.25% potassium feldspar, roughly 1.3% calcite and 1.3% aragonite, and a little over 1% illite muscovite, with only trace amounts of other phases. The dune sand is slightly more mature. It is approximately 94% quartz. It contains about 1.95% plagioclase and about 1.6% potassium feldspar. It has roughly 0.5% calcite and 0.2% aragonite, about 2.4% illite muscovite, and trace heavy minerals. We see calcite and aragonite, the two common calcium carbonate minerals associated with shell fragments and other biogenic debris. Here, the marine sample carries the stronger carbonate signal, with roughly 1.3% aragonite and 1.3% calcite. The dune sample still contains carbonates, but at lower levels, about 0.2% aragonite and about 0.5% calcite. That pattern fits what we saw in the field. The swash zone is where shell and other biogenic material is constantly being broken, rolled, and mixed into the sand. The dune, which sits above the reach of the waves, receives only aeolian shell input and gradually loses some of that carbonate as wind resorts and thins the sediment. So at the bulk scale, we have a very quartz-rich, chemically mature sand, with subtle but real differences between the marine and aeolian environments, and a clear marine fingerprint in the form of shell-derived carbonates concentrated closer to the active surf zone. Next, we will look at the very fine fractions, first under 4 microns, then under 2. In both less than 4 micron fractions, clay mineralogy is dominated by illite. The marine sample contains about 14% kaolinite, and the dune sample about 19%. Together, this illite-kaolinite mixture is consistent with a temperate to warm, moderately leached source terrain. In the less than 2 micron fraction, the marine sample is 69% illite, 17% kaolinite, and 14% chlorite. The dune sample is 84% illite, 10% kaolinite, 5% chlorite, and 1% smectite. The dune fines are more strongly illite-rich, with only a trace of smectite, while the marine fines carry a slightly larger proportion of kaolinite and chlorite. This pattern points to a moderately weathered, recycled sediment system. with chlorite indicating a modest mafic or low-grade metamorphic contribution and only limited development of swelling smectite. Taken together, the less than 4 micron and less than 2 micron clay mineralogy describe a moderately weathered, low expansive, illite-rich coastal sediment package. Geologically, this is consistent with a recycled coastal system derived from mixed but not deeply lateritic source rocks. In real estate terms, it supports a narrative of low expansive clay risk but non-negligible fine fraction control over drainage, radon generation, and environmental behavior, all of which can be managed once they are measured and understood. Next, we move from clay mineralogy to the electrical activity of the clays, measured as cation exchange capacity, or CEC. Despite being so sandy, the Matagorda sediments are not chemically inert. When we measure CEC, the marine sample shows a surprisingly high value for a sand, around 14.7 milliequivalents per 100 grams. That exchange capacity resides in the thin clay fraction and in coatings on the sand grain surfaces, tiny sites where cations can be held and exchanged. The dune sample has a much lower CEC at about 4.7. In both samples, the principal exchangeable cation is calcium. Recall from the mineralogy that the dune sample contains far less calcite and aragonite, the main calcium suppliers. Sodium adsorption ratio, or SAR, or SAR, indicates how strongly sodium competes with calcium and magnesium for exchange sites on the clay and silt surfaces. Elevated SAR values, especially where clay is present, can promote dispersion, surface crusting, and pore infiltration. In the marine sand, the SAR is about 14.4, slightly above the conventional sodic threshold of 13. Sodium occupies a meaningful portion of the exchange complex. In this setting, the sample sits in the active oceanic swash zone, with sodium chloride constantly washing through, so an elevated SAR is expected. It is best interpreted here as a process indicator of sustained marine sodium loading. Combined with a small but real clay fraction, it shows how a sand can still develop dispersion and surface sealing tendencies when sodium is dominant and calcium is not maintained. In the dune sand, the SAR is about 0.9, well below sodic thresholds. Sodium is present but not dominant, and is likely reduced by rainwater leaching when the profile is not directly influenced by oceanic waters. Dispersion risk from sodium alone is low, although the sand's lack of cohesion and high permeability still require attention for erosion and rapid drainage. For a floodplain field, an engineered fill, or an irrigation district, these numbers matter. A soil or fill with marine-like SAR values is more likely to crust and shed water unless calcium is replenished and structure is protected, while a dune-like material is more likely to accept and transmit water rapidly, with little crusting but also limited natural storage. Water content in our samples refers primarily to hydroxyls in the lattice, where OH groups are bonded inside clay and oxide frameworks, and, in more active clays, to interlayer or adhered water that sits on or between clay layers and is released in stages as temperature increases. Free pore water has already drained before testing, and contributions from carbonates and gypsum are subtracted. The size of this bound water fraction is a quick indicator of how much water can be stored within the mineral structure of a soil or sediment. In clay-rich, especially smectitic materials, a larger bound water fraction signals greater potential for shrink-swell behavior in seasonal, climate-driven volume change, higher compressibility and long-term settlement under loads, and stronger sorption and chemical reactivity for nutrients and contaminants through increased cation exchange capacity. It also implies a more complex thermal response, with greater scope for phase changes and microcracking if the material is strongly heated, for example during wildfire or around hot infrastructure. The same increased water holding capacity that can be hard on foundations under cyclic wetting and drying can also help buffer soil moisture for vegetation during dry periods, even though not all of that stored water is directly available to plants. In short, water content is an important factor to understand because it tells us how much water is tied into the mineral framework itself, how strongly that framework will respond to loading, heating, and drying cycles, and how active the soil will be chemically and mechanically over time. For the Matagorda pair, that bound water fraction is essentially zero. The marine sample calculates at minus 0.4%, a small negative value that reflects analytical noise around a truly dry sample, and the dune sample is about 0.22%, also functionally dry. In practical terms, both are almost pure quartz framework sands with only a trace of structurally bound water in thin clay and oxide coatings. That means very low shrink-swell potential, low compressibility related to clay fabrics, limited sorption capacity compared with a clay-rich soil, and a relatively simple thermal response. It also means there is little internal buffering of moisture for vegetation. These sands drain and dry quickly, and their behavior is controlled far more by porosity, permeability, and organic management than by water held inside the mineral structure. Elemental sulfur from the bulk analysis is about 200 parts per million in both the dune and the marine swash samples. That is a real but low background signal, and we cannot tie it to a single mineral. To see whether that sulfur is present as soluble sulfate salts, we ran the hydro extraction in distilled water. In both samples, sulfate in the extract was below detection. That result tells us there is no significant pool of readily soluble sulfate minerals such as gypsum or the nardite in these sediments. Instead, the sulfur is most likely distributed in thin coatings and films on grains, minor organosulfur, or very fine sulfides that do not release measurable sulfate under a gentle distilled water leach. These sands carry a light marine sulfur fingerprint, but not enough active sulfate to behave like a strongly sulfate-rich soil or to drive strong sulfate salinity or concrete attack on their own. The nardite is the anhydrous, or water-free, form of sodium sulfate, with the formula sodium sulfate. It commonly forms as a soluble evaporite salt in arid or saline settings and can hydrate to mirabolite, sodium sulfate 10 hydrogen oxide, expanding and contributing to salt weathering of stone, brick, and concrete. The absence of detectable sulfate in our hydro extraction means there is no meaningful reservoir of easily dissolved salts like gypsum or the nardite in these sands, and therefore no significant sodium sulfate crusting or sulfate attack risk originating from these sediments themselves. Next, we look at shrink-swell behavior, which is crucial for engineering. The marine sample has a very low shrink-swell index and a modest water content under test conditions. Also, the dune sample shows essentially no measurable shrink-swell capacity at similar water content. Combined with the clay mineralogy, this confirms that both sands are non-expansive, structurally friendly materials. They do not want to heave foundations, jack sidewalks, or crack slabs as moisture changes. The trade-off is that, because they are so open and well-drained, they also have very little natural ability to hold water at the surface. Moisture infiltrates quickly. That is excellent for reducing ponding and surface runoff, but it also means that anything spilled or leaked at the surface can enter the subsurface quickly and travel along those high permeability pathways. When we pull all of this together, the two samples give us a coherent picture. The beach and the dune share a common sandy framework, 90+% sand, almost no silt or gravel. The swash zone holds a mixed fine and medium grain population. The dune pushes sorting and porosity to the extreme. Both are quartz-rich, mature sands with shell-derived carbonates, especially in the marine setting. The clay fraction is small, non-swelling, and stable. Permeability and porosity are high, especially in the dune, which makes both units excellent conduits and storage zones for water. And even in this sandy context, there is enough cation exchange capacity to make these sediments chemically active. In other words, the Matagorda beach dune system is not just a strip of beige on a map. It is a dynamic, porous, chemically active barrier built, grain by grain, by waves and wind. And it plays a central role in how water, salt, and any introduced contaminants move between the Gulf, the bay, and the land behind the island. In the next stage, we can take this textural and mineral framework and ask a deeper question. What does the elemental geochemistry of these sands tell us about their sources, their evolution, their role in coastal resilience at Matagorda Bay, and their potential value as a source of critical elements in mining interest? That does not mean we are about to start mining Texas beaches, but it does mean we can evaluate whether these sediments carry any meaningful resource signal in addition to their coastal and environmental roles. In the ores and mines section, the goal is not to declare these sands an ore body, but to ask how a miner or critical minerals geochemist would read the elemental data. We group elements by how they are used in industry and by the minerals that tend to carry them, then look for any signs of enrichment above normal crustal background. If a signal is strong, it might point to a heavy mineral placer, a strategic metal byproduct, or at least a material that deserves closer investigation. If the signal is weak, that is also useful. It tells us these sands behave more as ordinary construction materials than as ore. Our first group is the refractory and alloying elements: titanium, zirconium, hafnium, niobium, tantalum, and their higher temperature cousins. These are high-strength, high melting point metals used in advanced alloys, aerospace components, industrial tools, and strategic defense applications. In the marine sample, hafnium and zirconium stand out, reaching roughly 53 and 39% of their crustal reference levels. Titanium is present at about 7%, and niobium and tantalum each at about 5%, while tungsten, ruthenium, osmium, and iridium are at background or below detection. This pattern indicates a light but real heavy mineral signal, likely carried by grains such as zircon and related phases, yet still well below the concentrations associated with an economic mineral sands deposit. In the dune sample, the same refractory and alloying elements tell a very different story. Titanium is modestly enriched at about 58% of its crustal reference value, but zirconium and hafnium spike to roughly 880% and 1137% of crustal levels. Niobium and tantalum are present at about 55 and 45%, while tungsten, ruthenium, osmium, and iridium remain at background. This pattern points to a clear concentration of zircon and hafnium-bearing heavy minerals in the dune sands, with only moderate support from niobium-tantalum phases. It is not an ore body, but it is a meaningful heavy mineral signal, showing how wind winnowing on the beach ridge can quietly upgrade critical elements compared with the adjacent marine swash zone. For the marine sample, the rare earth elements form a low but consistent background pattern. Lanthanum through lutetium range from about 8 to 19% of their crustal reference values, with the light rare earths, lanthanum, cerium, praseodymium, neodymium, at the upper end around 14 to 19%, and the heavy rare earths mostly between 8 and 15%. This broad, gently light Re-skewed pattern is what you would expect from a dilute mix of Re-bearing accessory grains such as zircon, monazite, or apatite scattered through an otherwise quartz-rich sand. In resource terms, this is not an economic rare earth deposit. The concentrations are far below ore grades. However, the coherent lanthanide pattern confirms that the marine sand does carry a measurable Re-fingerprint, useful for provenance work and for comparing the swash zone to the more strongly upgraded heavy mineral signal in the adjacent dune. In the dune sand, the lanthanides are substantially elevated compared with the marine swash zone. The light rare earths from lanthanum through samarium cluster around 40 to 50% of their crustal reference values, while the middle and heavy rare earths climb higher, with dysprosium to lutetium mostly in the 60 to 100% range and ytterbium reaching about 100% of crustal levels. This systematic uplift across the whole lanthanide series, and the relative strengthening of the heavy rare earths, is consistent with wind winnowing concentrating Re-bearing accessory grains such as zircon, monazite, and xenotime in the dune ridge. It is still far below economic ore grades, but it clearly shows that the dune environment upgrades critical rare earth elements relative to the adjacent marine sands and carries a meaningful geochemical fingerprint of those strategic materials. In the marine sand, most of the classic battery metals are at or below crustal background. Lithium, nickel, copper, zinc, molybdenum, and cesium are effectively zero on this normalized scale, and cobalt is only about 4% of its crustal reference value. The main feature is manganese, which sits close to crustal levels at about 94%, with smaller contributions from yttrium at about 12%, strontium at about 11%, magnesium at about 2%, and aluminum at about 9%. In the dune sand, the battery and strategic elements show a very different pattern from the marine swash zone. Lithium, nickel, copper, zinc, and cesium remain at or near background, and cobalt is only about 8% of its crustal reference value. Manganese and vanadium are moderately enriched at about 27 and 14%, and chromium reaches roughly twice crustal levels. The standout feature is molybdenum, at about 25 times its crustal abundance. There are additional, smaller but clear enrichments in yttrium at about 58%, scandium at about 9%, manganese at 27%, vanadium at 14%, chromium at roughly twice crustal levels, magnesium at about 4%, strontium at about 10%, and aluminium at about 8% of their crustal values, while beryllium remains at background. This pattern points to a genuine but selective concentration of strategic elements in the dune sands. Molybdenum is strongly upgraded, and yttrium, scandium, chromium, and related trace metals are all clearly elevated, most likely hosted in the same heavy mineral and oxide phases that carry the rare earths. It is not an economic battery metal ore body, but it clearly shows that wind winnowing on the dune ridge can quietly enrich specific strategic elements well above their levels in the adjacent marine swash sand. In the marine sand, most tech and precious metals sit at or near crustal background. Gold, silver, palladium, rhodium, indium, tellurium, and selenium are effectively zero on this normalized scale. The standout is platinum, at about 4 times crustal abundance, 400%. Rhenium is also clearly elevated, at about 286%, and silicon, with all the sand, is expected to be above average, and it is at 157% of its crustal reference level. Germanium is around 67%, gallium about 11%, and phosphorus about 4%. In absolute terms, these are still trace concentrations, far below ore grades, but they show that even this clean marine sand carries a small platinum-rhenium high-tech metal fingerprint in its fine heavy mineral and oxide fraction, rather than being a purely inert quartz sand. In the dune sand, the tech and precious metals are expressed much more strongly than in the marine swash zone. Gold is close to twice its crustal reference level at about 196%, and silver is the clear standout at roughly 8 times crustal abundance, around 800%. Platinum, palladium, and rhodium are at background. Among the high-tech metals, gallium is about 11% of crustal levels, germanium about 67%, rhenium about 286%, and silicon about 158%, while indium, tellurium, selenium, and phosphorus remain near zero on this normalized scale. These are still trace concentrations rather than ore grades, but they show that the dune ridge quietly concentrates a small suite of precious and high-tech metals in its heavy mineral and oxide fraction compared with the adjacent marine sand. In the marine sand, the mine environment and radioactive elements are present at low background levels. Uranium is about 15% of its crustal reference value and thorium about 13%, giving a modest but clearly measurable radioactive fingerprint without approaching ore regulatory concern levels. Barium stands out a bit more at about 45% of crustal abundance, consistent with trace barite or barium-bearing coatings in the heavy mineral fraction. Antimony, bismuth, arsenic, thallium, cadmium, mercury, and lead are all at or near zero on this normalized scale, indicating no elevated signal for the classic toxic metals in this marine sand. In the dune sand, the mine environment and radioactive elements are more strongly expressed than in the marine swash zone. Uranium is about 89% of its crustal reference value and thorium about 61%, giving a noticeably stronger UTH signature. Barium is about 34% of crustal levels, and lead is about 50%. Antimony, bismuth, arsenic, thallium, cadmium, and mercury are all at or near zero on this normalized scale. These concentrations are still well below ore grades or obvious contamination levels, but they do indicate a higher background for naturally occurring radioactive materials and lead in the dune ridge, something that would matter for radon potential, mine environment screening, or any future concentration of these heavy minerals. In the marine sample, the ore element enrichment and phase behavior chart shows that all 5 ore element groups are very close to background. The rare earth elements score about 0.02, battery and strategic elements about 0.01, tech and precious metals about 0.09, mine environment and radioactive elements about 0.05, and refractory and alloying elements about 0.01 on a scale from 0 to 1. All of these indices sit well to the left of the red threshold line, indicating only trace enrichment. Taken together, this means the marine sand carries a weak but measurable fingerprint of ore-related elements, mainly in scattered accessory grains and thin coatings, but no group approaches the level where the material would behave like an ore body. Phase behavior is dominated by dilute, background distributions rather than discrete, self-supporting ore minerals, and from a mining or environmental standpoint, this horizon reads as a geochemically clean marine sand. In the dune sample, the ore element enrichment and phase behavior plot shows a clear step up from the marine sand, but still short of true ore behavior. All 5 groups are enriched relative to the marine swash zone, with battery and strategic elements and refractory and alloying elements coming closest to the ore-like threshold. That pattern means the dune ridge is genuinely upgrading a suite of strategic and high-temperature metals into a heavier mineral fraction, but the enrichment is still modest. The elements are concentrated enough to matter for geochemical and mining environment screening, not enough to classify the dune as an economic ore deposit. Group 1 rare earth elements, lanthanides, score about 0.08. Group 2 battery and strategic elements, the strongest signal, at about 0.28, just to the right of the red reference line. Group 3 tech and precious metals, about 0.15. Group 4 mine environment and radioactive elements, about 0.11. Group 5 refractory and alloying elements, about 0.22, just below the red line. In the marine sand, the phase partitioning assessment shows that any ore-related elements are almost entirely carried by the coarse fraction, not by clays. All of these values lie well below the 0.3 reference line, so the marine sample behaves as a clean sand with only weak enrichment in the coarse heavy mineral fraction and essentially no clay-hosted ore potential. All clay-hosted indices are essentially zero, aside from a very small battery metal term at 0.0113. The coarse fraction indices are noticeably higher than in the marine sample, with battery metals 0.2721 and refractory, alloying elements 0.2088, the strongest, but none exceed the 0.3 threshold line. The Ore and Mines review shows that Matagorda Beach carries a clear heavy mineral and strategic metal fingerprint, but not an ore deposit. The dune sands do upgrade several groups of elements relative to the marine swash zone: zirconium, hafnium, molybdenum, yttrium, scandium, rare earth elements, and even small amounts of precious and high-tech metals. However, those enrichments are still at trace to background plus levels, well below grades that would support mining. The ore element indices stay far to the left of the ore threshold, and the phase partitioning analysis shows that these elements live in a thin, coarse, heavy mineral fraction rather than in any massive, self-supporting ore phase. In practical terms, Matagorda Beach is a scientifically interesting, slightly enriched heavy mineral system, valuable for understanding coastal processes and geochemical pathways, but not likely Texas's next big mining site. To get radon trapping and invasion, you need both a source and a pathway. The pathway is often called the chimney. Both sites have a radon chimney score of 1.0 because the sampled layer is a clean, sand-rich horizon with high porosity and permeability. That kind of material behaves like an open conduit. If radon is generated anywhere in or below it, the gas can move upward quickly through the connected pore space and into buildings or other enclosed spaces. The radon source score then tells us how much radon is likely to be generated in the material itself. At the marine site, the source score is low, 0.14, so this horizon is mainly a pathway. The larger concern is radon feeding into it from deeper or adjacent units, which is why deeper testing and indoor radon checks are recommended. At the dune site, the source score is much higher, 0.775, reflecting more uranium and thorium in the dune sands. Here the same sandy chimney is both a generator and a pathway, so the dune horizon is treated as radon sensitive and merits subsurface characterization plus indoor testing with ready mitigation. At Magnet we track many mineralogical pathfinders and ratios, but we highlight radon because it is one of the newer environmental concerns that directly links subsurface geology to indoor air risk. At Magnet Geological, most of the focus is on geology and inorganic geochemistry, but every evaluation also includes a screening step for mobile organic contaminants. For the marine sample, the organic hydrogeochemical panel shows no common organics detected. Semi-volatile herbicides, pesticides, and solvents are all below reporting limits, as are THMs, disinfection byproducts, and VOCs related to fuels or solvents. In this case, there is no evidence of anthropogenic organic contamination in the sampled horizon, and no organic-specific action is required. For the dune sample, the organic hydrogeochemical screen tells the same story of a clean profile. Semi-volatile herbicides, pesticides, and solvents are all reported as none detected, and there are no detectable THMs or VOCs related to fuels or solvents. In other words, the dune horizon shows no common anthropogenic organic contaminants in the pore water, and no organic-specific mitigation or follow-up sampling is required on the basis of these tests. For agriculture and green space, we look at samples in two ways: what they can give to plants and what they might take away from them. On the nutrient side, we track major and trace elements that support growth: phosphorus, potassium, magnesium, calcium, sulfur, zinc, copper, manganese, boron, and others, and estimate how much of each is actually readily plant available and long-term resource availability. On the toxin side, we screen the same material for metals that can damage crops or soil health, such as lead, cadmium, chromium, excess manganese, and aluminum, and we flag any that approach concern levels. This combined nutrient toxin panel lets us see whether a horizon behaves more like a neutral rooting medium, a nutrient source, or a soil chemistry risk. For the marine sand, the agricultural nutrient panel shows that this horizon is a very lean rooting medium with only a few strengths. Plant available calcium is about 5.6%, sulfur about 10.6%, and boron about 4.2%, with smaller contributions from magnesium, manganese, zinc, and copper. Phosphorus and potassium are present but at less than 1% plant available. So this sand by itself would not sustain crops without fertilizer or organic amendments. On the toxin side, cadmium, arsenic, mercury, selenium, thallium, and nickel are not detected. The main elements to watch are manganese, chromium, and aluminum, which are present in the fine fraction but at low plant available levels, giving a modest toxicity score rather than a strong hazard. Overall, the marine horizon behaves more like a chemically clean but nutrient-poor sand than a true agricultural soil. In the dune ridge sample, the sand behaves more like a very light but workable turf soil. Phosphorus, calcium, and sulfur are present in meaningful plant available amounts, and micronutrients such as zinc, copper, manganese, and boron are clearly detectable. Potassium and magnesium are modest, so a Bermuda grass surface here would respond to standard turf management. Routine nitrogen and potassium fertilization, occasional magnesium as needed, and deliberate building of organic matter to help this very sandy profile retain water and nutrients. For a natural green space or playground beside a housing development, the toxin picture is mixed but manageable. The most hazardous metals, cadmium, mercury, selenium, and thallium, are essentially absent. Arsenic, lead, chromium, manganese, and boron are moderately enriched in the coarse fraction, but remain in a range consistent with a managed green space rather than an industrial contamination site. The practical guidance is straightforward: maintain a dense grass cover, minimize bare dusty areas, and, for a high-use play area, consider blending in a shallow layer of cleaner topsoil at the surface as an added margin of safety. Chemical fertilizer is a quick, soluble boost. It delivers nitrogen, phosphorus, and potassium straight to the grass. But it does little to change the sand itself and has to be reapplied. Basalt is a slow geological amendment. As it weathers, it releases calcium, magnesium, potassium, and trace nutrients. Helps buffer acidity, adds fine particles that improve structure and water retention, and can also help sequester carbon by reacting with carbon dioxide. Because basalt can carry trace metals, each source should be tested and compared with the existing soil so it does not double existing contaminants or introduce new ones. In practice, the strongest strategy is usually a blend: fertilizer for immediate turf response, basalt for long-term soil improvement and resilience. This is the recommended fertilizer program for the marine sand sample. Focusing on Bermuda grass in a green space, the crop requires about 100 pounds N, 24 pounds D phosphorus pentoxide, and 100 pounds potassium oxide per acre. To achieve that on this very low fertility sand, the program applies 150 pounds N, 110 pounds D phosphorus pentoxide, and 120 pounds potassium oxide per acre, about 150% of the nitrogen requirement, more than 4 times the phosphorus requirement, and 120% of the potassium requirement. There is no sulfur, magnesium, or micronutrient supply in this blend, so the Bermuda grass cover is maintained almost entirely by repeated fertilizer inputs on an otherwise nutrient-poor marine sand. For dune ridge sample, focusing on Bermuda grass as a green space cover, the crop needs about 100 pounds N, 24 pounds D phosphorus pentoxide, and 100 pounds potassium oxide per acre. The fertilizer program applies 150 pounds N, 105 pounds D phosphorus pentoxide, and 165 pounds potassium oxide per acre, about 150% of the nitrogen requirement, more than 4 times the phosphorus requirement, and 165% of the potassium requirement. It supplies no sulfur, magnesium, or trace metals, and delivers boron at more than 20 times the Bermuda requirement. So even though the dune sand carries more native nutrients than the marine sand, the Bermuda grass still depends on a strong, front-loaded fertilizer program, with notable oversupply of phosphorus, potassium, and boron. Basalt is an alternative to annual magnesium fertilizer. This program is based on a 6% self-activating weathering rate, so each application continues to release magnesium for years. The yellow bars show a front-loaded basalt plan, 50,000 pounds per acre in years 1 and 2, then 20,000 pounds per acre in years 3 and 4, with essentially no new basalt after that. The blue line tracks total plant available magnesium in the root zone, and the green line shows the magnesium deficit closing. As the basalt weathers, magnesium availability rises, the deficit reaches balance by the end of the decade, and from about year 5 onward the existing basalt supplies 100% of the Bermuda grass magnesium requirement each year. The idea is that an early investment in basalt turns a chemically poor marine sand into a more complete and resilient soil with its own long-lasting magnesium bank, instead of buying fertilizer forever. For the dune sample, the basalt program is lighter because the sand already has some magnesium. Here we also use basalt as an alternative to annual magnesium fertilizer, again assuming a 6% self-activating weathering rate. The yellow bars show a smaller front-loaded plan, 25,000 pounds of basalt per acre in years 1 through 4, then essentially no new basalt after that. As the basalt weathers, the blue line, total plant available magnesium, climbs and then levels off, while the green line shows the magnesium deficit steadily shrinking and moving toward balance by the end of the decade. From about year 5 onward, the existing basalt meets 100% of the Bermuda grass magnesium requirement each year. So this green space can rely on a modest early basalt investment instead of ongoing magnesium fertilizer, with the soil continuing to improve long after the last application. As we pull back from the numbers and return to the shoreline, remember where this all began. 2 small samples from the edge of the Matagorda jetties, one taken in the active swash zone, one lifted just a few yards away from a low dune. On the surface they looked identical, clean, pale sand, but the maps and images you have seen, from the Google Earth fly-in to the close-up dune photos, remind us that every position on this coast sits in a different part of the geologic and hydraulic system. By following these sands through texture, porosity, and permeability, we saw why water, air, and gas move so easily through them, and why they can drain or dry out faster than most soils. The mineral and clay pie charts showed that both horizons are quartz-rich and non-swelling, with only minor clay to hold water. The geochemical panels then revealed how trace metals and rare earths partition between the coarse grains and the clay fraction, and how the dune carries a modest but real heavy mineral population while the marine sand remains geochemically cleaner. From an environmental perspective, the radon indices and toxin tables place both horizons in a manageable risk category, provided they are treated as permeable, gas-connected sands rather than as traditional agricultural soils. Nutrient and toxin scores for the marine horizon described a chemically clean but nutrient-poor foundation. The dune horizon, in contrast, behaves more like a very light turf soil, with usable phosphorus, calcium, sulfur, and micronutrients, but also a moderate load of arsenic, lead, chromium, manganese, and boron tied mainly to specific mineral grains. The fertilizer tables showed what it takes to turn these sands into productive green space. For Bermuda grass, both horizons rely on strong, front-loaded fertilizer programs that oversupply nitrogen, phosphorus, and potassium to compensate for weak native fertility. Finally, the basalt scenarios offered a different pathway, using the tested basalt as a slow, self-activating amendment that releases magnesium at roughly 6% per year, gradually closing the magnesium deficit and building a long-term nutrient bank in the root zone. In the marine sand, that means transforming a chemically poor substrate into a more complete soil. In the dune, it means reducing future dependence on magnesium fertilizer while the soil continues to improve. Taken together, these 2 small sand samples demonstrate how a beach that looks simple on the surface can hold a complex story about texture, minerals, nutrients, toxins, and long-term management. The same laboratory tools that help us search for ore deposits can also help city planners, engineers, and landowners design safer, more resilient coastal green spaces, grounded not in guesswork, but in the actual behavior of the sand beneath our feet. Thank you for your attention. This mineralogy and geochemical work was completed for Geoscientists Without Borders project building resilient coastal communities at Matagorda Bay, and for Mr. Collier, a graduate researcher at the University of Houston. For questions or project inquiries, Mr. Johnson can be reached at magnetgeological.com.